Here is an interesting application of an exponential model, something called the Newton's law of cooling, because traditionally it is applied to the study of the temperature of an object that is cooling in a colder environment. Okay, so we in Alberta are all familiar with the idea of being very nice and warm in the middle of the winter and going outside where it's really cold, and then the body temperature is going to cool down fairly rapidly at the beginning and then probably slower. Okay, in fact, usually we're well protected, so that doesn't really reach the extremes that it could. But if you take an object like a glass of water, better still a plastic cup of water will shatter, and if you take it outside in a cold temperature, then of course the temperature of the water will cool and tend toward the temperature of the environment, become equalized with the environment. So what we're going to be looking at is the following problem. Let's say that we have an object and we're placing it in an environment which is at a constant temperature called the TE, temperature of the environment. Okay? What we're interested in knowing is how the temperature of the object is going to change as a result of this cooling effect. Okay? And what we're going to be doing is we're going to assume that the difference in the temperature between the environment and the object is going to follow an exponential model, meaning that this difference in temperature is going to change at a rate which is proportional to the difference itself. Now, if you think about it, that means that if that difference is very big, then it's going to change rapidly. And on the other hand, if the difference is pretty small, then it's going to change very slowly. It looks reasonable. Well, you really need some more information to assume that this model is true, but it certainly makes sense and it is reasonable. Assuming that it is true, then we know that the solution is going to be that the quantity itself, which is the difference in temperature, notice, is going to be proportional to an exponential function of time, okay, where of course k is the same k as the original function. So it's just an exponential model. Okay. The one thing that we need to be careful about is that the fact it's an exponential model applied to the difference in temperature. Now, in order for this to work, we're also going to assume certain things which in reality are not always true. So this law of cooling is going to give us an approximation in the best circumstances. For instance, this assumes that the environment does not change temperature. Now just think about taking a cold potato and putting it in a pot of boiling water. Yes, the potato will heat up, but the water will cool down. Okay, so this assumption is going to fail right away. What we can do is we can assume that there is constant heat going into the water, which will keep its temperature constant, or maybe we can assume that there is an awful lot of water, or for instance in the case of us going outside in cold weather, there is so much cold air around us that it's really the insertion in the cold weather of another object is not going to make any difference. Okay, but again, this is an assumption. Also, we're going to assume that there are no other factors that is going to interfere with the process. I talked earlier about some heat that keeps the water at a constant temperature, fine, but if that heat is actually going to raise the temperature of the water, then this model goes out the window, and so on and so on. So notice again, there are all kinds of assumptions that we make. Any one of them doesn't work, the whole process, the whole computation is not valid. Okay, so as I said, in the best circumstance, this is going to be an approximation. Let's notice a few things about this Newton's law of cooling and its solution. Okay? So first of all, notice that when I take the derivative of the left-hand side, I can use the addition rule of derivatives and say that that's the same thing as the derivative of T, the temperature of the object with respect to time, minus the derivative of the environment temperature with respect to time. But the environment temperature doesn't change, therefore that derivative is going to be 0, and therefore that left-hand side really just represents the rate of change of the temperature of the object. And what I'm saying is that this is going to be proportional to the difference in temperatures. Okay? So the differential equation we're dealing with tells us that the difference in temperature relates to the rate of change of the object's temperature. Okay, so we're dealing with two different things. One is the temperature of the object, the other one is the difference between the temperature of that object and the environment. And we need to be careful in order to make sure that we use the proper piece of information and the proper interpretation for the differential equation to work and its solution to be usable. Okay? So for instance, when I look at the solution, we can write the solution as T, which is the temperature of the object, is equal to C e to the kt plus the temperature of the environment. But what is c? Remember, c comes from that original differential equation which deals with the difference in temperatures. That means that the c that we have in this particular model refers to the initial difference in temperatures, not the initial temperature of the object. Okay? So this is again something that needs to be kept in mind in this situation as well as in any other variation of the exponential model or other models we're going to be looking at. We always have to be very careful in interpreting all the quantities involved in the proper way, especially when we're making variations of the basic idea.